Section 6.4, Derivatives of Logarithmic Functions. Your homework is problems 3 through 11 odd, 43 through 53 odd, and 71 through 81 odd. So to begin, we're going to work with our logarithmic functions and their derivatives, and we're going to be using a lot of those properties we learned from the previous section. To begin, the derivative of a logarithmic function is ln of x. The d dx of ln of x is equal to 1 over x. That's our derivative. But that's only when our argument is x. If our argument of our log, like the x is our argument, is something other than x, we need to consider chain rule. So in other words, let's take a look at the second box here. We have 1 over our function, whatever x is, and on top, or times on the side, the derivative of it. Let's do an example. So these two boxes are the same, but I like how that second one's written better. So we're going to take the derivative of y equals ln of x cubed plus 1. So let's take our derivative, so we get y prime is equal to. So our derivative, since we have ln, would be 1 over, and then whatever we're taking the ln of goes in the bottom, our denominator. So we have x cubed plus 1. And then I need to multiply it by whatever is in the parentheses. What is our logarithm argument? In this case, it's x cubed plus 1. We're going to take that derivative. So I'll write a prime to know that I still have to take the derivative. I'm just saying it up for us. So our answer will be 1 over x cubed plus 1 times, use power rule, 3x squared. And we were just multiplying fractions, so you can write it as over 1, multiply across. Your final answer can be 3x squared over x cubed plus 1. That's our derivative, and that's how we work with derivatives and logarithms. Let's do another example. So here being asked to find the derivative of ln sine of x, same as before. So because we have ln, our derivative of our argument will be 1 over whatever we have. In this case, it's sine of x. Remember, then you have to multiply it by the derivative of our argument. So I'll just write a prime since we're setting it up. Okay, so we have 1 over sine of x times the derivative of sine is cosine. And we can multiply them across so that we have cosine over sine. And your trigonometry comes in handy. Sine over cosine is tangent, so cosine over sine is cotangent of x. And that's our derivative. Pretty impressive, right? All right, let's continue with our next example. F of x equals the square root of ln of x. So just for the sake of preparing ourselves, let me write our radical as a rational exponent so that we have the ln of x raised to the 1/2 power. Okay, so initially what's on the outside, remember we always work outside in, is not your ln. So really what we have here is chain rule. But within this chain rule, we're going to use our newly found derivatives of ln's. Okay, so chain rule, derivative of the outside, which is just power rule. So we have 1/2, and 1/2 minus 1 gives us negative 1/2 ln of x. So that's our outside. Now we need to take the derivative of our inside. Now I didn't take the derivative, I'm just going to set up for derivatives. So I wrote a prime as a note to ourselves that we need to take the derivative. Let's go ahead and apply the derivative. So we have 1/2 ln of x raised to the negative 1/2 power times the derivative of ln x is 1 over x. Okay, from here let's just clean it up. So I want to write that negative exponent in the bottom. It's a radical, so I want to write a square root. So I have 1 over 2 square root of ln of x times 1 over x. So we have 1 over 2 times x square root of ln of x. And everything's multiplying, so you can write it any order you like. Don't feel like one is better than the other. You can write 2 times square root of ln of x times x, and that's okay too. And just remember, multiplication has no order. Alrighty, next problem. Find the derivative of ln of x plus 1 divided by the square root of x minus 2. So I saw this one initially. I took an approach, and now that I'm looking at it after recording the previous section, I'm considering a different approach, but I'll stick with what I have. Okay, so let's go ahead and use our new rule of ln. So our rule is we have 1 over our argument. So we have x plus 1 divided by square root of x minus 2. And then I have to take the derivative of our argument. So x plus 1 divided by square root of x minus 2. Okay, and I need to take that derivative, right? So I'll write a prime. As we get ready for that, for this derivative, we see that we're going to have to use quotient rule. So everything you learned in your previous calculus class doesn't go away. It's just used better, right? You're more comfortable with it. You're not. It's something new. Now, just to remind you of quotient rule, we have the derivative of our numerator times our denominator minus our numerator times the derivative of your denominator divided by your denominator squared. Okie dokie. Let's go ahead and work that out. So for this part right here, we have 1 over, so it's just the reciprocal. We get square root of x minus 2 divided by x plus 1. Okay, now let's go ahead and find that derivative. So I have times. Multiply, let's take that derivative. So our numerator derivative of our numerator, which is our f, is just 1. 1 times our g, which is square root of x minus 2, minus our numerator, which is x plus 1, times our denominator, our derivative of our denominator. So we have 1/2 times x minus 2 raised to negative 1/2 times 1. Right, so that was a little chain rule there. Divided by our denominator squared. So square root of x minus 2 squared. And you see that the square and the square root are gone. All right, now we have to clean it up. As we get ready to clean it up, let me just give you a little hint of our distribution. So we have this, and we can distribute this in, right, to each one of our terms. We have 2 terms. We have this term here and this term here. Now we have square root of x minus 2. Think of that as a base with an exponent. So if I have so your distribution hint. So if I have square root of x times square root of x, what does that simplify to be? That's x to the 1/2 times x to the 1/2. According to your rules of exponents, if they have the same base, we add their exponents. So we have x 1/2 plus 1/2, which is just x to the first power. So it would be no different if we have the square root of x minus 2 times the square root of x minus 2, because I have that exponent of 1/2, that's just going to be x minus 2, right? That's what I was trying to get to. All right, so when I multiply this times this right here, the radical goes away. And when I multiply this times this over here, we add them. 1/2 plus -1/2, that's 0. So they're gone. That one's going to go away. All right, so what do we have? We're left with x minus 2, since they're raised to the 2/2 power, which is 1, minus, we have the 1/2 times x plus 1. That 1/2 plus -1/2 is 0, so we have x minus 2 raised to the 0 power. That's why I crossed it off. And then times 1 is itself. Divided by, what's our denominator? We have x plus 1 times x minus 2. Cool beans. All right, we can go ahead and distribute that -1/2 so that we have x minus 2 minus 1/2 x minus 1/2 divided by x plus 1 x minus 2. Let's clean it up. We get 1/2 x minus 5/2 divided by our denominator. We can factor out a half from our numerator. And we can write that 2 in the bottom. There we have it. This one was complex. Now we're going to do some other problems where we differentiate LNs and different and more complex type of functions. And we can use our properties of logarithms to break them down and make it easier for ourselves. And as I was setting up to write this problem up with us, for this video, I realized I could have taken a different approach. But we'll see that in the future. All right, example, find f prime of x. So the derivative of f of x equals ln of the absolute value of x. All right, when we're considering absolute values, we have to consider what can x be. So this x right here can be either positive or negative. So let's just blindly, in a sense, set up our both possibilities, positive and negative. So positive when x is greater than 0, and negative when x is less than 0. So our function x, you can have ln of a positive x if x is greater than 0, or the ln of a negative x, right, when our x is less than 0, negative. So if I take the derivative of each one separately, the derivative of ln of x is 1 over x, and we said that's when x is greater than 0. The derivative of ln negative x would be 1 over negative x times -1, right? That's when x is less than 0. Let's clean it up. So we have 1 over x, and a negative times a negative is positive, so we have 1 over x. So even when I have my positive option and when I have my negative option, I still have that same argument for ln. So our big conclusion here is that our derivative is 1 over x for all x when x is not 0, since we have a denominator of x. That brings us to our next little theorem. The derivative of the absolute value of ln of x, or ln absolute value of x, that's better, is 1 over x. And therefore, we can consider our integral. So the integral of 1 over x dx is ln of x plus t. Let's go ahead and find this integral, the integral of tangent of x dx. And when I first saw this problem, I thought, well, this is something that we probably have from our Calculus 1 class, so we were given a chart of all these definitions and integrals for trig functions. And oddly enough, tangent isn't included. Tangent is one of those secret ones, I guess. So this one's not in our list of trig integrals from Calc 1. All right, let's go ahead and set up this integral. So I want to find tangent, but we don't know the integral of tangent. We know the integrals of are the values for sine and cosine, so let's rewrite it. We know tangent is sine over cosine, so we have sine of x divided by cosine of x dx. Okay, let's take the integral. Now, because we're working with two different arguments or functions of x, where one is the original and the other is a type of its derivative, we can use u substitution. So that we have u is, all right, so this is tricky because you can, unless you're super careful, you can make the error of picking the harder one. So let's think of why would be the easier one. So we want to have an argument of u, but I don't want to have u equals u over dx because we never have had a 1 over dx type of situation. So we want to make sure that our u is in the denominator, right? So u should be our denominator function, so cosine. U is cosine of x. When I did it the first time, I just did the wrong one. All right, so we have u, our derivative is du is equal to negative sine dx. So we can make the replacement where u is cosine. And let's make this change here. Let's write negative du. Let's multiply a negative for both sides. Sine of x. So now we can say that sine of x is equal to negative du. All right. So now let's make that change. So our integral will be 1 over u times du. And the negative is a constant, so we can move that outside. Okay, let's integrate. According to our definition right above, the integral of 1 over x is ln, absolute value of x. So here we have ln, absolute value of u, plus c. And for this one, we had a negative. Don't forget your negative. So I have negative ln, absolute value of u, plus c. Let's make the replacement. We said u was cosine of x. So our answer is negative ln, absolute value of cosine of x, plus c. And actually, now that we see how this happened, you should add this to your list of trig integrals. So the integral of tangent x is ln secant of x. Moving forward, general, logarithmic, and exponential functions. Rule for taking the derivative of a function who has a base other than 10 and e says the derivative d dx of log base b of x equals 1 over x times ln of b. Now, just like everything, you have to consider chain rule. So we have to consider the derivative of our argument. So to this, I would add times x prime. Or our initial notes had it as well, they did differently. They would use u or function notation. So I think prime notation makes it easier, at least for me to keep track of. And I wrote a little hint there. Remember to also take the derivative of the argument if there is something other than just an x. And we'll see that in this very next example. Find the derivative of log base 10 of 2 plus sine of x. So what makes this different from our other problems is that I have the log of a argument or of a base that's not. That's actually written, so we have to consider it. Okay, so according to our definition above, I want to write it as 1 over, and I want to have my argument, which is 2 plus sine of x, and then multiply it by our b. And our b in this case is 10. Not just b, but ln of b. So ln of 10. And then we need to multiply our derivative or argument. So 2 plus sine of x, I need to remember to take the derivative of u. So the derivative of it, so let's write a little prime notation. Let's take the derivative. So I have 1 over, let's rewrite that, 2 plus sine of x times ln of 10 times, well, 2 is just 0, derivative of sine is cosine, so we're just left with the cosine of x. Let's write that together. So we have cosine of x over 2 plus sine of x times ln of 10. Moving forward, the derivative of an exponential function. So if I have something where my exponent contains my variable, to find the derivative of that, so d dx of b raised to the x power is equal to b to the x power times ln of b. And again, we need to take the derivative of our argument. So x prime. Now, our notes don't write it that way because if x is x, then the derivative is 1. But what about when it's not just x? Okay, so let's do an example. So let's take this derivative. So I have my base b, and this is my exponent. Let's follow our rules. So first part is just our function itself. So just rewrite it. So that we have 10 raised to the x squared times the ln of our exponential base. Our base here is 10. So I have ln of 10 times the derivative of our exponent. So we have to take the derivative of that x squared. I'll write a little prime since we're just setting it up. Okay, let's work it out. So I have 10x squared times ln of 10 times 2x. And that's our answer. Now they're being multiplied, so you can write them in any order. We can write little dots in between them, not write any dots in between them, write parentheses. Depends how you like your answer to look. Next one, integration formula for exponential functions. So if I'm looking for the integral of an exponential function, so if I have something raised to the x power, our integral would be equal to b to the x power divided by the ln of b plus c. All right, so take a look at this example. So here we have the integral from 5 to 0 of 2 to the x power dx. Okay, so our rule says I have a fraction. And the numerator, we have the same thing. So we're going to have 2 to the x power. In the denominator, we're going to have ln of our base. And for this one, our base is just 2. So I have 2 to the x power divided by ln of 2. And that's our integral. Now, this is not an indefinite integral. It's defined. It's a definite integral. So it's from 5 to 0. We don't write c. We don't write plus c. We actually work it out. So I have 2 to the 5th power divided by ln of 2 minus 2 to the 0 power divided by ln of 2. All right, 2 to the 5th power is 32. over ln of 2 minus 1 over ln of 2. They have the same denominator. 32 minus 1 is 31. 31 over ln 2. Next, we have logarithmic differentiation. Now, this is where I said that that first example, or one of those earlier examples, could have been done differently, and this is why. The calculation of derivatives is complicated functions involving products, quotients, or powers can often be simplified by taking logarithms. The method used in the following example is called logarithmic differentiation. So for this example, let's differentiate y equals x cubed, x to the 3/4 power times the square root of x squared plus 1 divided by 3x plus 2 to the 5th power. All right, what makes this complicated is all these arguments of x. You can actually proceed and you take the derivative using your Calc 1 training. You would use quotient rule to begin, and when you start using quotient rule, within that you would have product rule. You would also have chain rule, and you can do it, but it's a complex problem. So we can use our ln's, our logs, to approach this differently. All right, since we have an equation, equations give us a bit more freedom because we can do the same thing to both sides. So let's go ahead and take the log or the ln of both sides. So I have ln of y is equal to the ln of x to the 3/4 power times square root of x squared plus 1 divided by 3x plus 5 raised to 2 raised to the 5th power. Okay, I forgot y, ln of y. Now the reason we took the ln of both sides is because I can use my laws of logs to break down the problem. So to begin, I see it's being divided, so I can go ahead and use subtraction. So I can break it down to be ln of the numerator, x to the 3/4 power times the square root of x squared plus 1 minus the ln of 3x plus 2 to the 5th power. We still have ln of y. Okay, and I can use, they're being multiplied. So because they're being multiplied, I can go ahead and use that summation law of logarithms. So this here becomes the ln of x to the 3/4 power plus the ln of the square root of x squared plus 1 minus the ln of 3x plus 2 to the 5th power. We still have ln of y. Lastly, I can use my exponent rule to move those exponents and make them constants. So let's go ahead and do that next. So I have the 3 over 4 ln of x plus, we know that radical is the exponent of 1/2. So 1/2 ln of x squared plus 1 minus 5 ln of 3x plus 2. And we still have ln of y. Now, nowhere did we actually take a derivative. All we did here was simplify our problem using our laws of logarithms. Or in other words, we didn't simplify, we expanded. And we did this so we can now take a derivative. All right, if we take the derivative, now we included y into our argument, so we have to go ahead and take our derivative implicitly. So we have to use implicit differentiation. so that we have the derivative of ln of y is 1 over y times y prime equals 3 over 4 is just a constant, so I can ignore that. The derivative of ln of x is 1 over x plus 1/2 is just a constant. I can disregard that. The ln of x squared plus 1, so I have 1 over x squared plus 1. Don't forget to take the derivative of the denominator, which is just 2x minus 5 times 1 over 3x plus 2 times its derivative, which is just 3. All right, and there we have it. Now last piece, I want to find the derivative for x, not y. So we want y prime. So let's get rid of this y by multiplying both sides by y. And we're left with y prime is equal to 3 over 4 times 1 over x plus 1/2 times x squared plus 1. You can write that 2x in the numerator, 2x. You can clean up that first one too. So we have 3 over 4x. And we're in the third term minus 5 times 3 is 15, 3x plus 2. And what is y? Well, we have what y is equal to. Y is equal to our entire initial argument. So let's just write that for y. X to the 3/4 power times the square root of x squared plus 1 divided by 3x plus 2 to the 5th power. And this right here is our derivative. All right, moving forward. So we also have a set of steps that we can use when we're trying to use logarithms with our differentiation. So your steps are: 1, take the natural logarithm of both sides of the equation so that we have y equals f of x, and use properties of logarithms to simplify. So in other words, take the ln of both sides. So you're going to have ln of y equals your ln of whatever your argument is. 2, differentiate implicitly. So you're going to involve your y in your derivative. So that we're going to have, for y, if y is by itself, we're going to have 1 over y times y prime. Your derivative implicitly, and then everything else in terms of x. 3, solve the resulting equation for y prime. So we just multiply y to both sides to get y prime by itself. Remember to replace with original function. Alrighty. Now moving forward, something you know already is your power rule. So if n is any real number and f of x equals x to the nth power, then we can take the derivative, which would be f prime of x would be n times x to the n minus 1. So it's just your power rule from Calc 1. Remember, you bring your exponent down, and then you subtract 1 to your exponent. And we're just mentioning it because we're working with all these exponents. We want to make sure we have everything kind of neatly presented. So it's a highlight of what you learned in this section. So when we're working with derivatives, remember, if you have a constant base and a constant exponent, your derivative is 1. For example, 2 squared. What's the derivative of 2 squared? Well, they're just numbers, so it's 0. Second, if I have a variable base and a constant exponent, that's just power rule. Something like x squared. How do you take the derivative of x squared? That's just 2x. The other two are new. A constant base and a variable exponent. That's our new rule we learned. Consider the example we did, 10 raised to the x squared power. And lastly, when you have a variable base and a variable exponent, that's also new, and we'll see that in this new example. This is where we can use logarithms. So last example for this section. Differentiate y equals x to the square root of x. All right, well, the problem here is that we have our exponent, well, our variable is in our exponent's place. Luckily, we can use our laws of logs if we apply logs on both sides. So that we have the ln of y is equal to the ln of x raised to the square root of x power. Why did we introduce logarithms? Because according to my exponent rule, I can move my exponent to be my constant. Well, not my constant, but my leading coefficient in a sense. All right, now that we have that, we have ln of y is equal to square root of x times ln of x. Now I can take the derivative because now I just have two things in terms of x multiplying. I can just use product rule. Okay, let's go ahead and take the derivative. Implicitly. I misspelled implicitly. Alrighty, let's take our derivative so that we have the derivative of ln of y is 1 over y. Because we're working with x, we're going to write y prime is equal to, use product rule, the derivative of square root of x is chain rule, so we have 1/2 times x raised to negative 1/2 times derivative of x, which is just 1, minus, or I forgot to write my second term, ln of x plus my first one, which is square root of x times our derivative of our second argument of x, which is ln of x, so it's 1 over x. All right, let's clean it up. So I have 1 over y times y prime is equal to, let's clean this up. This is just 1 over square root of x. So I have 1 over square root of x. I have a half, so a 2. And ln of x is in the numerator, so ln of x. There we go. That looks much nicer. Plus, on our other one, we have square root of x over x. Okay, let's multiply y both sides so I can cancel that out. And we're left with y prime. Our derivative is equal to ln of x 2 over square root of x plus square root of x plus x divided by x. And then I need to write y. What is y? Well, we have y right here. Y is x raised to the square root of x. And there we have it. That's our answer. All right, that was section 6.4, derivatives of logarithmic functions. Thanks.